on down.
Okay.
All right.
I always yield.
First off, everyone hear me okay? Yes. All righty. Thank you all for coming this afternoon. Although the title may make you a little bit uncertain, and certainly after some of the things we heard from Dr. LaPointe last week, it's clear that there are problems on the coral reefs that we have here in Florida. I'm going to give you a little bit more data and background on how those problems have developed in this past decade in particular. But then for the second half of this talk, really try to focus on the bright spots, the hope for the future, what we think we can do to make things better. All righty. I'm going to start off with what I'm not going to talk about today. And I got this as a tip from Randy Posh. If you guys have not had a chance to check out his last lecture, look it up online, ask someone to find it for you. It's amazing. So, here at Harbor Branch, we study a number of different things, but I focus on benthic ecology. So I'm not going to talk about pretty little fishies. I'm not going to talk about menacing sharks and genius dolphins, even though I love all of these things. I'm going to try to convince you that corals are just as interesting as these charismatic megafauna. Next thing I'm not going to talk about, because my mom told me it wasn't polite, is politics or religion. And one question in particular that I'm not going to address is, do I or do you believe in global warming? And that's because global warming is not a matter of belief or a matter of faith. It's a scientific fact. We know it. So I'm not going to address that question in this talk. I'm also not going to talk about the cause of coral reef decline. And Dr. LaPointe can attest to this, as most people who work in coral ecology, we're always being asked, well, what's the real problem? What is it? What's the one thing we can fix? And it's not that simple, although we'd love it to be. There are multiple causes, and I'm going to address a couple of those different causes this week. Last week, you heard Dr. LaPointe talk a bit about some coral diseases and nutrient problems as well. And lastly, I'm not going to talk about throwing in the towel. Often you hear people say, well, it's just going all to hell. There's nothing we can do. We might as well refocus our efforts elsewhere. Florida reefs are lost. That's not the case whatsoever. I'm going to try to demonstrate to you tonight that there's a lot of reason that we should keep working to protect the reefs we have. Alrighty. The reefs we have are fairly extensive. They extend over 220 miles from St. Lucie Reef, just south of here down in Stewart, all the way out to the dry Tortugas about 70 miles west of Key West. Now, that's not an entirely contiguous reef tract. There are areas where there's breaks in that reef, but along that entire region, the relative diversity and abundance of corals is fairly good for a region of this size. Our reef is fairly young, only about 5,000 to 7,000 years old. So since the last ice age is when our reef has started growing. And almost this entire area, save for some sections in Broward County, has at least some level of protection around it. Those levels vary to complete research only, no entry zones, to, yes, it's a park, but it's entirely not enforced and anyone can do whatever they want. There's a range across that area. The vast majority of the coral reefs that lie in Florida are in the Florida Keys Reef Tract, extending from Biscayne Bay down to Key West, and then there's a break and out to dry Tortugas. Most of that area is fairly protected. There are special protected areas within that where there's no take whatsoever. So this is the only slide, I promise, that I'm repeating from last year. Talking about the importance of our coral reefs ecosystems. And I've tried to add a bit of information as well. They're a high center of productivity. And what I mean by high productivity is that two things. Number one, they're fixing a lot of carbon. So they're actively taking carbon dioxide from the atmosphere and depositing it in a reef structure. That's a good thing for us at a climatic scale. In addition, they're not just taking it out of the atmosphere, but they're physically converting that carbon into useful energy in the ecological sense. So in these areas, we have lots of productivity just like you would in a forest. Also similar to that forest idea, they're high centers of biodiversity. The reason biodiversity is really important, it's not an aesthetic idea. it's not, oh, there's an amazing diversity of life for us to see, but rather the more biodiverse a system is, when changes occur, be it climatic changes, large-scale global changes, etc., the more different kinds of organisms and the more different genes that those organisms have, the greater the likelihood that at least some of those organisms will be successful and survive. So we won't lose that system. They're very important for us in terms of coastal protection, especially from hurricanes. We have a huge tourism industry here, estimates of $1.2 billion annually in the Florida Keys. And there's lots of potential pharmaceuticals, again, related to that biodiversity issue. When you have lots of different organisms living in a very small spatial extent, often those organisms, especially those benthic organisms, not the ones that are up swimming around, but the ones that are stuck on the bottom, they have to compete with one another, and that competition often results in a lot of novel compounds that they produce to try to fight one another chemically. Okay, so let's set the stage a little bit for the past decade, and a touch of this will be a little bit going back over some things we heard last week, but I wanted to emphasize this point that up until 2000, there were some crazy things happening. Number one, the most dramatic cold wave that's ever hit Florida was back in 1977. We had snow in Miami, and this was the first case of large-scale mass mortality in corals. About 6 years later, we had a diadema urchin die-off. Diadema urchins are very important herbivores on the reef, and nearly 98% of the diadema Caribbean-wide were lost due to one pandemic in 1 year, and we're still not recovered from that event. Throughout the 80s, at a number of different points, again Caribbean-wide, there were outbreaks of white band disease. White band disease affects both staghorn and elkhorn corals, also known as the acroporids or Acropora species. And then in 1995, there was another strong disease that was found called white plague. Main difference, and I've left a little reveal here, is that in white band, you get a band of bleached tissue between this healthy coral tissue and the barocoral skeleton. White plague, on the other hand, is completely a distinction between all barocoral skeleton and healthy tissue. That tissue just actively sloughs off right there at that point. White plague was not only more voracious, it had a much broader host range. Instead of affecting just the 2 species of acroporids, we know that it infects at least 58 different species here in the Caribbean. And we also know that white plague has a number of different forms. These diseases are very difficult to identify in the field. Often we give them names like this, obviously, that give you some kind of indication of what they may look like if you were to see them. We think that there are a number of different bacteriological agents that cause white plague disease. So while they were lumped together in 1995, it was likely that many different diseases were all hitting corals at the same time. And then lastly, in 1998, throughout the Caribbean and here in the Florida Keys, we had another mass mortality event, this one linked to an ENSO, or El Nino Southern Oscillation event. And what differentiated this 1998 event from some of the previous events were that huge colonies of coral were being lost on an unprecedented scale. So, up till 1998, this picture is looking fairly grim. I'm going to work from about 2000 forward, focusing on that next decade. In response to a lot of these changes, if we look at just 1996 through 1999 in the Florida Keys, at living coral cover, this is the percent of the ocean floor that's made up by live coral. You can see that it was only about 12% in 1996. And historically, the level of living coral cover in the Florida Keys hovered anywhere from about 15, maybe up to 20% at times. So it wasn't terribly low in 1996. But between 1996 and 1999, we lost nearly half of that. The mean living coral cover in the Keys by by August of 1999 was just below 8%. 8% of the entire bottom covered with living coral. In contrast, areas of the Indo-Pacific can have more than 100%. So much coral growing that it's actually layering on top of each other. So this is where we were at. Because of that, there's been a number of different monitoring programs that have been enacted. Dr. LaPointe talked about his monitoring program at Lou Key. I'm going to talk about a monitoring program that was developed by the Florida Keys National Marine Sanctuary. This was an annual program that was developed to look at coral community structure, the abundance of that disease and bleaching and the potential effects on the coral. And although we started it in 1998, I'm going to focus on just this last decade, from about 2000 until now. We've partnered with a number of different groups along the way. Back in 2000, I must admit that I was still an undergrad, so when they first started this program, I wasn't involved yet. But since then, I've become involved, and every year we get to go out on a NOAA ship called the Nancy Foster, and we get to go to 50 different locations in the Keys. And at each of those different locations, we track the same corals over time to see how they've done in that previous year. Now, a little bit more background on what bleaching is and what disease is and how they kind of get muddled, but we should differentiate them. Remember, bleaching is that breakdown in symbiosis between the algae that live inside the coral, the zooxanthellate dinoflagellates, and the coral itself. There's evidence on both sides that coral stress and algal stress result in the breakdown of the symbiosis. So it's not simply the corals kicking the algae out, or it's not simply the algae deciding to leave. It's probably a combination of both, and chemical cues suggest that both are going on. Now, when bleaching occurs, they can recover. The corals can uptake dinoflagellates from the environment and repopulate themselves in order to survive, or those few dinoflagellates that are left in the living coral tissue can begin to grow and divide so that the coral gets its color back, gets its mechanism of energy back. However, if this bleaching condition persists, usually more than about a week, the coral essentially runs out of energy. The algae are what are providing those corals energy, and without the algae, corals don't have the ability to survive for a long period of time. They effectively starve. Disease, on the other hand, is active tissue loss. And diseases often can persist for years without completely killing a coral colony. One of the biggest differences between disease and bleaching is that bleaching is generally seen as a physiological response in concert with environmental variables that are going on. Whereas disease we consider something that's transmissible from one coral to another. Could be a bacteriological agent, could be a fungal agent, etc. Here in this example right here, this is black band disease, one of the ones that I work on most often. You can see bare coral skeleton, here's the white area, a black band along the disease front, and healthy coral tissue down here in that golden color. So this microbial mat, composed primarily of cyanobacteria, colonizes the surface of a coral, starts to degrade that coral tissue, and then marches stepwise, migrating horizontally along that coral head, completely dissolving any of the coral tissue that's there. It moves fairly slowly, but again, it's very persistent. So we've been looking at both of these things. And specifically, we're looking at the spatial patterns and temporal patterns, aka coral epidemiology. We're looking at the occurrence of those diseases. Are they there or not? The prevalence of those diseases, and by prevalence, it's just like in us. What's the percentage of the population that's infected at any given time? And lastly, severity. Now, severity in humans is usually a little bit more easy to discern. In corals, we use metrics like how much coral tissue has been lost, or how quickly is the disease advancing on an individual colony. In addition, we don't just want to know what the patterns are, we want to know why those patterns are occurring. What environmental cues or what particular host factors or pathogen factors are resulting in epidemics across our corals. And so these are the scientific questions behind that Florida Keys National Marine Sanctuary survey. Now, Throughout our time that we've been doing this survey, we started to see changes in the sea surface temperatures at different areas throughout the state and throughout the Caribbean. We know that temperature is a problem, but it's not just the absolute maximum temperature, rather it's the time over which corals are exposed to that temperature. If temperature spikes for a brief period of time and then drops back down, most corals can do just fine. However, if the temperatures increase at least 1 degree above the maximum mean average from the summertime, corals begin to get stressed out. And as those high temperatures persist, 1 week, 2 weeks, 3 weeks, we start to see the corals break down. They get stressed out. The measure of this persistent heat has been developed by NOAA. It's called degree heating weeks. In other words, the number of weeks cumulatively, a running average, during which temperatures have been elevated to a level that we know would stress out corals. And so this starts in October, in September. You can see it's transitioning all the way up until just yesterday. And so right now, there's no heating whatsoever. We'll talk about that in just a little while. But typically, our degree heating weeks and the area or the durations of maximum coral stress are not during the hottest month of the year. They're after the hottest month of the year, where we've peaked temperature-wise, we're slowly falling off, but the accumulated stress on the corals is persisting. So we've been following this trend and trying to determine if this change in degree heating weeks, this relatively high temperature persisting for a long period of time, is having impacts on coral health and disease. Here's a simpler way of looking at that degree heating weeks. Here we're going from 2001 through 2009, and this is simply a numerical value of the number of persistent weeks that we've been exposed to high temperature. So ranges from just over 1 in 2002 all the way up to nearly 9 in 2005. In fact, 2005 was the hottest year on record ever in the entire Caribbean. It was not only hotter than it had been before, but it was hotter for longer than it had ever been before. And so if we look at what was going on in terms of coral disease during this time, here is the relative percentage or the prevalence of black band disease among susceptible species over this same time period. We don't have any data for 2003. We didn't get out that year because of some weather that we had to deal with. But you can see that there's variability in the numbers of corals that are diseased. So in other words, some corals do survive. They don't just get knocked out. And if we were to overlay our degree heating weeks over this same time period, you'll notice that in 2005 and in 2007, when we had the highest levels of degree heating, that's also when we see the highest abundance of disease. That's when the most coral mortality is going on. So there's a clear link between elevated sea surface temperature and coral disease and mortality. One of the most disturbing aspects of this pattern is that traditionally, corals got a time out. Every winter, fronts would push through, the degree heating issue would go away, and most diseases would physically disappear from the reef altogether. So corals that had experienced disease, and maybe half of that coral had died, that coral had a chance to not have disease, potentially grow back, maybe even reproduce. However, since 2005, we've started to see a new trend. Whereas almost all of the black band diseases would disappear in the winter prior to 2005, since 2005, we've been tracking black band at a few reefs down in the southern Florida Keys. And while there's still a seasonal pattern, more disease in the summertime, less disease in the wintertime, now not all of the disease is disappearing completely during the winter. So a lot of these corals aren't getting that break. They're continuing to be infected. They're continuing to lose tissue throughout the entire year. We think this is probably going to be a problem in the next 2 or 3 years as well. Alrighty. So we have this heating issue going on, particularly in 2005 and 2007. So who knows what the Earth does when it gets too hot? What's nature's air conditioners? Hurricanes. In 2004 and 2005, I don't have to remind any of you that they were some of the most active storm years on record. 2004 was particularly bad here with Hurricane Charlie, Hurricane Francis. I know these are almost 4-letter words around here. I apologize. Jean, and Ivan. Now, all of these made direct hits on the Florida mainland, but if you notice where the tracks go, most of them avoid the Florida Keys Reef tract. The only one that we really get a direct hit with is Charlie, here with a direct hit on the dry Tortugas. The eye of Charlie physically passed over the dry Tortugas. Amazingly, despite all of this hurricane activity in 2004, the impacts on coral were relatively minimal. Francis, Jean, and Ivan had effectively no impact on any of the reefs south of Miami. There were minimal impacts on St. Lucie Reef, some sedimentation, some smothering, but overall, these huge storms came through. Corals were able to do just fine. 2005, again, hottest year on record, and we have some of the worst hurricanes on record as well. First one to come through was Hurricane Demise. Remember, Demise is the one that uprighted the Spiegel Grove that Dr. LaPointe talked about last time. And despite having the ability to turn a ship that was more than 100 feet down completely upright, the impact on corals was relatively minimal. There were some staghorns and elkhorns that were lost in the lower Florida Keys. Most of that was related to some bleaching and some sedimentation. But again, in general, huge hurricane comes through, the impacts on corals is relatively small. Same was the story with Katrina and Rita and Wilma. We got painted across South Florida, hurricanes going on either side of the Florida Keys, and despite all of this activity, while there was some bleaching observed and there was some level of coral mortality observed, none of them were anything like what we'd seen in 1998. In 2005, in other areas of the Caribbean, up to 50% of corals were lost. Down in the Virgin Islands, for example, they had a bleaching and disease event where at least half of the remaining acroporids died. So we got lucky in 04 and 05. So that begs the question, are these hurricanes angels or demons? We know that hurricanes can provide direct physical damage to corals. They can break coral pieces off. They can deposit sediment on corals that smothers them. That sediment can be whipping through so fast that it scours the tissue right off of a coral skeleton. But hurricanes also function as air conditioners. They reduce the water temperature in the areas that they travel through. And so if we look here, in August of 2005, when Hurricane Katrina came through South Florida, if we look right before Katrina, again, this map is showing the relative degree heating weeks. So the more orange the color, the hotter it's been and the longer it's been hot. Right after Hurricane Katrina came through, the Florida Keys is nice and cool again, as is the entire rest of the Gulf where Katrina traveled. So while hurricanes can potentially cause a lot of direct impacts, they also have this secondary, potentially even favorable role, where they're reducing local temperatures, preventing bleaching, and preventing outbreaks of disease. Again, if we look at 2005, every time a hurricane comes through, the sea surface temperature drops. Katrina comes through, sea surface temperature drops. Rita, drop. Wilma, huge drop. And so what we see is that up until Katrina, we were on this trend of, oh gosh, it's going to be a horrible summer. Degree heating weeks are on the rise. We're only into August. We're expecting things to be horrible. Hurricane Katrina came through. It cooled things off, and effectively corals were spared because of it. So we have all of these things going on over time. And the amazing part is that while we saw dramatic losses from 1996 through 1999 in this monitoring program, since 2000, the relative losses of coral cover have been fairly non-existent. We've gone from approximately 8% to approximately 6.5% as of last year. None of those being statistically different from one another. So, all is well. The world is saved. Corals are fine. Not exactly. Has coral loss in the Florida Keys stabilized? If we were looking just at coral cover, you would say yes. It appears to have stabilized, with the exception, of course, of a few weeks ago, this new cold water mass mortality event. Those of you that are here for Dr. LaPointe's talk may have heard me answer a question about the estimated percentages of coral lost. At that time, I was relaying numbers of 20 to 26% from those who run the Bleach Watch program. After talking with Corey Walters, a colleague of mine down there, she estimates that at least 75% of the nearshore corals in the lower Keys have been lost. So we're having this issue of, instead of corals being able to live in a moderate tropical environment where temperatures have stabilized, instead global climate change is causing higher maxima and lower minima than we've seen before. The combination of those is resulting in coral death. In addition, not only has living percent coral not really stabilized, we also see continued reduction in the average size of those corals. So even though corals might not be dying en masse, corals are experiencing partial mortality. And we're losing some of these big old sentinels, and they're being replaced by relatively small individuals. The real problem with that is those large colonies are the ones primarily responsible for coral reproduction. Small colonies allocate most of their energy towards just surviving, not getting sick, not getting overgrown by something else. It's not until you're a big old guy that you can really start to pump out coral gametes. And so if we are losing all of these large individuals, we know that in the future, coral reproduction will be limited. We still have ongoing and new disease outbreaks. In 2008, we documented what we believe to be a new disease in the dry Tortugas. We're calling it Beggiatoa white syndrome. It essentially looked like someone had taken a huge pot of really loose plaster of Paris and just poured it right over huge coral colonies, dripping white sloughing areas all over these 300, 400-year-old colonies. We're still having persistent paling and bleaching, especially recently. Some of the earlier monitoring programs, including that one run by the Florida Keys National Marine Sanctuary, only scored bleaching. Is it bleached or is it not? As we started to understand that there's different grades of bleaching, you don't always lose all of your zooxanthellae, sometimes you just lose half. We started to score things like paling on quartile scales. 25% of the zooxanthellae lost, 50% of the zooxanthellae lost. And because we're looking at those finer scales, we're realizing that paling persists much more often than we'd previously appreciated. And lastly, kind of the elephant in the room is this potential unknown impact of ocean acidification. We know that one of the aspects of climate change is increased CO2 is going to drive changes in ocean chemistry and increase the acidity of the ocean. We're still not completely sure what all the biological impacts and ecological impacts will be as a result of this. So there's your not so good picture. The rest of this talk, I'm going to try to be a little bit more positive and talk about the new hope we have here in Florida. And I'm not kidding. We really have a town in Florida named New Hope up in the Panhandle. It's in the Panhandle, so we may not want to claim it, but it's there. And one of the things that gives us a little bit of hope is that we've seen sea urchin recovery, diadema recovery, in a number of different places throughout the Caribbean. Hasn't happened here in Florida yet. We know that diadema larvae have a fairly large dispersal capability. So if we're seeing improvement in other areas, we hope that eventually some of those larvae will make it to the Florida Keys and we might see improvements here as well. We also have had a lot of different strides with regard to improved sewage management. I know this borders on politics, but this is legislation, not politics. It passed in 2008, and the new rules, if we can stick to them, will mean no new outfalls whatsoever. At least 60% of our raw sewage will be reused by 2025, and effectively we would remove all ocean sewage outfalls by 2025. Whether or not we end up sticking to that, we'll have to wait and see. It'll, of course, depend on the political side of things. But as a bright spot, Delray Beach was the first, just in March or May of this last year. April 1st. Delray Beach was the first one to completely turn off their drain pipe. They were the first ones to cap and stop pumping their wastewater onto the reef. So we applaud them. The other thing to be excited about is acropora restoration. Both staghorn and elkhorn corals, those acroporid species, are listed as endangered, due in large part to the significant die-offs from white band and other white diseases. And right now, there's at least 82 additional coral species that are under consideration for endangered status by NOAA. Now, NOAA is not the one who actually decides, but they can make recommendations that are often heard. Some of those are here in the Caribbean. There are some that are in the Pacific as well. I think last week, Dr. LaPointe talked about the $3.3 million in surplus funding that's going to acropora restoration research. If you pull up that surplus funding, or excuse me, that stimulus funding directly from the federal government with other flow-through stimulus money through the state government, it comes out to just over $4 million, in fact. And there's currently 4 existing coral nurseries here in Florida. They're going to boost the output of those 4 nurseries and add 2 more, with the goal being by the end of next year, they'll be producing about 12,000 coral colonies that survive when outplanted in the wild. Now, we've been contacted numerous times about how is this going to affect the natural population. Time and again, stock enhancement projects have demonstrated that if you're not careful with the genes that you reintroduce into the environment, you can cause a whole lot of problems. And there's only recently been increased appreciation of this fact with corals. So Dr. Sarah Edge, one of my close colleagues here in the Robertson Coral Reef Program, has been working on looking at the gene expression of these corals to determine what's the optimum strategy for outplanting these guys. How do we make sure that what we're putting out there is not only not going to cause problems, but also ultimately be successful? So it's a good economic and ecological investment. The other exciting part of figuring all of this out is trying to understand coral recruitment. Coral recruitment, again, has been fairly limited, in large part due to the loss of those large individuals. So the relative number of coral larvae out there in the ocean with the potential of settling has started to fall off year by year. But if we can increase the probability that those larvae in the water column settle and survive successfully, we can increase the number of corals on a reef. So here's an example of coral spawning. Corals release their sperm and eggs up into the water column. They float up to the top where the sperm fertilize the eggs. A larvae is created, and eventually those larvae find their way back down to the bottom, to the benthos. And if all goes well, that larvae turns up on its end and metamorphoses into a little coral polyp. Right here in Fort Pierce, Raph, raise your hand for us. There he is. Raph Ritson-Williams, who works down at the Smithsonian Marine Station, has been working on determining what settlement cues these larvae are keying in on to determine where they settle. If we can determine effectively what those cues are, we can bait coral larvae into settling in good places. We can engineer habitats effectively so that we know that we're going to have increased success of recruitment. Alrighty. Now, the other aspect of this is if we're going to do all of this work to save corals, and we're going to do all of this work to outplant corals, part of it should be determining which of these corals are the toughest. And not just who's the toughest, but why are they the toughest. So even all the way up here at St. Lucie Reef. St. Lucie Reef is generally considered the northernmost extent of coral reef development in the Western Hemisphere. We're partnering with FWC to try to investigate the health status of corals on this marginal reef, and also what the effects of freshwater discharge from the St. Lucie Inlet are, because these corals are surviving through all kinds of hardship. They made it through the hurricanes in 2004. They made it through Tropical Storm Faye, where unprecedented amounts of water were dumped out onto the reef, and they're still going along just fine. In fact, not only are they going along just fine, they actually appear reproductively active. They have gametic development, so they're getting ready to spawn. We haven't witnessed them spawning yet, but we know that they do have gametes. Another thing I wanted to point out here is this: I'm way more resilient than you'll ever be. One of the buzzwords you'll often hear when people are talking about coral reef decline, coral reef health status throughout Florida is resilience. And again, resilience refers to not only the individual strength of corals, but again, that idea that if we have a diverse system, both at the species level and the genetic level, that system will be more resilient, more able to cope with change. Another way we've been looking for these toughest corals is more experimentally. So with some funding from the Mote Marine Protect Our Reef program and support from NSF for an intern here, Dan Rowan, who was with us last summer, we were able to get a bunch of corals from the Florida Keys National Marine Sanctuary Recovered Coral Nursery. When the Navy decides it wants a new dock, rather than scrap all of the corals that are on the old dock, the sanctuary sends a team in to physically chisel off by hand each and every one of those corals that's colonized along the wall. They then move those corals to a nursery in Key West Harbor, and they're available for potential restoration projects as well as experimental projects like this one. So we were able to get a number of these individuals from the Recovered Coral Nursery. We chopped up those individuals into little standard-sized pieces, and then we artificially killed them. We went out to the reef, collected a whole bunch of this black band disease, and we were testing three things actually. Number one, does disease change in response to temperature or light? Remember, we've seen a lot of evidence that temperature drives the prevalence of black band disease. And what we found is that only works up to a threshold. Once you get over about 28 degrees, it can keep on getting hotter and hotter and hotter and hotter, and the relative amount of black band doesn't change all that much. So it's a threshold system, not a linear system. We also were looking for which of these coral colonies responded the best to disease. So we were tracking the progression of this little clump of black band across the fragment, as well as any changes in the bacterial community, both within the disease itself and the bacteria that live on corals. Just like you, corals have a whole bunch of bacteria that allow them to be incredibly diverse in the amount of different things they can eat. We were looking at coral gene expression, again with Dr. Edge, and lastly looking at coral immune activity. What kind of immune proteins are these corals turning on in response to disease? And that's what Dr. Laura Midlar is at University of Texas, Arlington. So again, here's an idea of how they started out. Each of them had the exact same amount of disease placed at one end of the fragment. And here's an example of day 1, day 4, and day 7. And because it's a little hard to see, I'm just going to color it in for you. And what you can see is that from day 1 to day 7, the black band actively advanced on this coral fragment. We saw that in a number of fragments, but in some cases, the relative amount of black band progression was fairly slow. In other words, if the fragments that didn't have much black band progression may be tougher. So we analyzed this, and we compared our different colonies. We had 5 different colonies. These colors are just descriptors. They don't relate to the actual color of the colony. They're just tags we gave them. And what we found is that 2 of our colonies were very susceptible to disease, the red and the green colony. Orange was moderately susceptible, but the yellow and blue colonies seemed more resistant. The infection did begin, but it barely migrated across the colony at all. So what this means is that even within just Key West Harbor, there's differences between those corals that are conferring different response to disease. The question, of course, is why? And so there's a bunch of different possibilities that we're looking into. Number 1, are these colonies more susceptible to infection? Are they potentially predisposed to this higher rate? And there's a couple of different possibilities. Number 1, that variation could be different among completely different coral species. It could be that there's high levels of genetic difference in the species we looked at, this Montastria. Because we know there's relatively high levels of genetic diversity within that species, one of the possibilities is that those 2 that were very susceptible had genes that are not good for fighting black band, whereas those 3 that were more resistant have genes that are effective at fighting black band. So we're going to try to look at the genetic diversity between these and expand this project to look at different corals from different regions throughout the Florida Keys to see if we can identify susceptible populations or resistant populations. Now, just because they're susceptible or resistant, we're still not quite sure why. Again, it could just be that natural variability in their genes. Another possibility is they could have been previously damaged or previously exposed. Just like in us, there's a possibility that you acquire immunity through having a disease earlier, or conversely, sometimes it's easier to catch a disease the second time if you've already had it once, like dengue fever. So we don't know which of these 2 cases it is. We're going to look at both. And again, we're looking at a number of different molecular mechanisms to investigate that. One of the other bright spots for hope, in addition to finding out which corals are the toughest, is looking at mesophotic reef refugia. Mesophotic is a term that translates directly to middle light. So shallow reefs are those areas where we typically think of a coral reef. Bright, beautiful, clear water, right up on a crest, down in the Florida Keys, corals everywhere. As you move down a coral slope, the relative light availability starts to drop off very quickly, especially after about 50 meters or so, 150 feet. Below that zone, light's still available, but the relative amount and quality of light is fairly low. In those areas, corals persist. The question is, number 1, why? And number 2, if we have reduced thermal stress and potential reduced anthropogenic stressors on these deep reefs, then offspring from these reefs could restore some of our shallow reefs. This is an idea that has been batted around quite a bit. These deep corals would reproduce. Their larvae would swim up to the top of a reef and repopulate those areas of shallow reefs. We don't know for sure yet if this is a possibility or if this is happening. And so one of the things that we're doing as part of the new Cooperative Institute here at Harbor Branch, along with UNCW, and Dr. Pomponi talked about this quite a few weeks ago, is we've taken on a new mesophotic reef project where we're looking to both explore and characterize these new mesophotic reefs. What's their extent? How much coral really is there out there? And then determine the genetic and potentially physiological connectivity between these shallow and mesophotic reefs. We can look for similar genes in both the deep reef and the shallow reef, and if those same genes are transferring across that area, we can determine if there's a source of larvae coming from the deep into the shallow, or vice versa. It could be a source from the shallow going down into the deep. And lastly, if they are potentially an area for refugia, we want to know what their health status is as well. Are they threatened? Are they facing the potential same dramatic losses that we've seen in shallow water corals? If so, can we do things more proactively than we did with shallow corals to make sure the same thing doesn't happen on these deep ones? Alrighty, so all of these bad things are happening. All of these great new things are potential possibilities, but these are not going to be enough, and corals still need our help. So what can you do? What people always ask me. Number one, we need to reduce the pace of global climate change. Climate change happens. It's happened historically on the Earth for hundreds and hundreds of millions of years. The difference now is that the rate of global climate change is accelerating. So if you're interested in how you can do that, check out carbonfootprint.com. You can estimate how you yourself are contributing or helping the CO2 issue that we're facing. Number two, we know that we can reduce nutrient inputs. Nutrient inputs have been linked to increased rates of coral disease, decreased rates of recovery for corals that are damaged, and increased rates of macroalgal growth that can compete with corals. So simple things like don't fertilize your lawn, especially if you're someone like me who lives out near the beach. Most of the fertilizer you put on your lawn runs right on off. So rather than having that big, beautiful green lawn that we all aspire to and we all kind of harken back to when everyone lived up in the Northeast, plant things that are local. Try to use as little external inputs onto your property as you can. And if you're a dog owner, I know it's crazy, but compost your dog's presence for you, if you will. Responsible boating and diving is one that makes good sense. We still have a number of cases, usually over 50 a year, in the Florida Keys where we have pleasure boaters, of course not meaning to, but running aground, usually out of negligence. We still have a number of inexperienced divers that you'll see standing right up on a coral reef. And so simply education on how to be a responsible diver and how to be a responsible boater can help our corals. Also, well-engineered coastal development. Now, optimistically, I would say, hey, let's all move 30 miles inland. But that would make me quite a hypocrite since I bought a house at the beach not too long ago. And so rather than stopping or reducing coastal development, we need to think about how to engineer it in such a way that we are not causing excessive runoff in different areas. Keep the dunes, build back from the beach. Don't build a seawall, for example. Support marine protected areas. This is a fairly contentious one. It's starting to gain more and more public popularity. It still goes against a lot of people who are subsistence fishermen here in Florida. But marine protected areas can help to improve responsible boating. It can help mandate nutrient loads in those areas, etc. Another hard one, especially for someone like me who loves grouper. Avoid eating fish that we know are depleted, especially grouper. Grouper are one of the most overfished groups of fish anywhere in the Caribbean. So when you're at the restaurant and they offer you grouper, ask if you can switch your sandwich to a mahi sandwich. We know that mahi-mahi grow much more quickly. The reproductive rate is higher. The time from which they are juveniles until they reach maturity is much shorter. So they can recover more quickly than groupers can to fishing pressure by hungry humans. And lastly, learn more and share the knowledge that you have. A lot of people are great about learning things it's a lot more difficult to go out and deliver that message to other people. So I would encourage you all to do that. A place you can look for information that would help you to deliver that message is our website. And I'll be happy to take any questions after I thank some people. Of course, all of this work takes lots of effort. I'd like to particularly acknowledge those who work in the Robertson Coral Reef Program with me, Dennis Hanasak, Sarah Edge, and John Reed. There's a host of other people that help with this work. Our principal funding comes from the Banbury Foundation and to me anyway, the River Branch Foundation, so we thank those people for support. And I'll answer, well, any questions that you may have. Yes, sir.